seconds. 20 seconds. 9, 8, 7, 6, 5, 4, 3.
Well, you've all heard the expression, the camera can't lie, haven't you? Well, in this lecture, I'm going to be talking about colour, and I'd like to start off with a word of explanation. I think you know that these lectures are broadcast, and when they come to be broadcast, some people will be looking at them with colour television receivers, and some with black and white receivers. So I want to show you, first of all, what the people will see who have colour television receivers. And I have a little board here, a little sign, and we'll have a look at that. And you can probably just read that. You see, that's what I said, wasn't it? The camera cannot lie. And now we'll see what people will see who have black and white receivers. Well, they may read that as the camera can lie. Well, perhaps lie is rather a strong word. It's not telling all the truth, though, is it? The fact is that colour was missing. And in this lecture, I'm going to talk about what we have to do to send this other very important piece of information called colour. Colour is... I'll come to this very... Excuse me one moment. I'll have to answer this. Hello? I seem to have some nut here on the other end. He's telling me that something's landed in his garden. What is it? He says it's a funny object. It's a rectangular sort of box-like thing, but it might be radioactive or something from Mars. I do apologize for this. He says he thought he'd ring up the Royal Institution because they might be able to give him the right answer. What's worrying you? I see. How big is it? 18.72 centimeters long, 7.95 centimeters high, yes, 3.23 centimeters broad, yes, yes. Accurate, isn't it? Very. How much does it weigh? 42.79 kilograms. Oh, the weight of the thing. What colour is it? It's a bluey green. Look, if I'm going to tell you what it is, you'll have to do better than that. A bluey, what do you mean, bluey green? Well, there's no need to be rude. He just says if I think that he can describe a colour accurately over the telephone, I'm nuts. Look here. Oh, he's rung off. Well, there's the problem, isn't it, you see? He could tell me exactly what its size was, how much it weighed. He could go on and tell me anything about it that he could measure. Because when we stop to think of it, it's these measurable things that we can turn into electric signals that we put down wires. And if we can't measure it, we're not going to be able to send it. Well, these things we've been talking about, like sound pressure and the brightness of light, these things could be large and small, couldn't they? And we could control an electric signal and make it large and small to correspond with the variations of these sort of quantities. But what do we do about colour? Because colours aren't exactly large or small, are they? How do you turn an electric signal into something that's going to describe a colour? Well, this is the sort of question that Sir Isaac Newton asked, 300 years ago. he not only gave us the laws of motion, but he asked this very question: why is it that things are colored? Why is it, for example, if I hold up this book, you all see this, don't you, as a red book. Why is it red? Why is that girl's jumper purple? And I could go on, couldn't I? Why is that lady's jumper yellow? Well, it's no good saying that this is red because it's printed red and that's purple because it's dyed purple. We're running into this sort of question, why is it mummy, why is it mummy? And we're not going to get any answers, are we? We just get, well, that's the way it is, you see, it's painted that color. No, we have to go further than this. And Newton indeed did go a lot further than this, and he gave us the answer to the question, or he gave it pretty accurately. Before I discuss Newton's experiment, though, I'll show you what we're going to be talking about. As I've said before, the light waves are electromagnetic waves, and so they fall in the electromagnetic wave spectrum. And up till now, we've been talking about the radio frequency wave, and it's these frequencies going up to what they call the UHF we talked about here, and the super high frequencies here. And then it isn't long before we're into the infrared part of the spectrum, waves that we can't see but give out heat, or you can feel them. And just this little bit here, the bit we've got painted in this strip, is the visible spectrum. It's a very small part of the whole thing, isn't it? This, incidentally, you'll appreciate, is what we would call a logarithmic scale. You know, the logarithmic scale, I mean that equal distances every time is multiplying by 10. So these are very high frequencies. In fact, if we talk in terms of frequency, 10 to the power of 14 is 100 million megahertz. And you remember we were talking in our radio frequency transmissions of things like 100 megahertz, or perhaps even 600 megahertz. Well, these are 100 million. So they're very high frequencies. They occupy a very small part of the spectrum. In musical terms, it would be just 1 octave. In terms of wavelength, the longest wavelength, the red end, is about roughly 0.8 of a millionth of a meter, and the blue end, the short wavelengths, are about 0.4 of a millionth of a meter. And these are the electromagnetic waves that I'm going to be talking about that give us the sensation of color. Now, what did Isaac Newton do? Well, do you remember when I was talking about the centimeter waves, I used this wax prism, and do you remember I showed how the wave was bent? This wax was transparent to those centimeter waves. The waves went straight through, but the prism did slow them up, with the result that the waves didn't have to travel through very much in this part of the prism. They had to travel through a lot more here, and so the bottom end got slowed up, and the waves slewed around and got bent. Well, as I expect you know, and I'm sure you do, this happens with a glass prism. And now we're up at these very short wavelengths, the visible part of the spectrum, and this is a glass prism. And you see, we're going to shine through it, as Newton did, a thin slit of light. Now, he used sunlight, but we can't get any sunlight in here, so we're using a nice, powerful source of light here, and it's going through a slit, and if it wasn't for the prism, it would land up somewhere over there. But instead, it's going to land up on that screen. It's going to be bent. But the interesting thing is, different parts of the spectrum are going to be bent by different amounts, and this is what Isaac Newton found. We know now that the bending, to give it its correct name, the amount of refraction, depends on the wavelength, and we're going to find that the blue wavelength, the short ones, are going to be bent further than the long ones, and so we're going to get the colors that go to make up white light spread out. I'll be using in this demonstration some filters, and by filters, I simply mean this sort of thing. Now, if you hold that up to the light, it's just a piece of red glass, or it can be a red celluloid. Here's some celluloid. That's green, that's red, and whereas the book I held up reflected light, these ones, of course, transmit light. And you'll hear me using these words, reflection and transmission, quite a lot. So now I'm going back and I'm going to ask Mr. Coates to give us this source of light. We'll lower the lights and have a look at the visible spectrum. And here it is. All the colors of the rainbow, as we'd say. Starting from this end, we have red going through to orange, yellow, green, indigo, blue, and coming off here, violet and ultraviolet, which is invisible under normal circumstances. We might be able to have a look at it a little later on, and we'll see if we've got time. So this is the spectrum. Now, what I want to show you first of all is this point, that if I take this red book that I took before and hold it in this end of the spectrum, you see that very, very bright red line. You can see it on the monitors. That's very clear to us, isn't it? The book is reflecting that. Now, as I bring the book across the spectrum, it goes virtually black. In other words, it is only reflecting the red part of the spectrum. I'm going to ask Mr. Coates now to put in a red filter. Now, the red filter passes the red light and just a little bit towards the orange here, principally red, you see. And so the book shows that same red band just as it did before. In fact, you wouldn't really know I wasn't holding up a white piece of paper. Now, put the spectrum back, and there it all is. So the book is just reflecting that little part of the spectrum. Just let's do the experiment, as it were, another way around. We'll use another color this time. First of all, this is white, so is the screen, so you would expect it just to reflect all the colors of the spectrum. But I'm going to now ask Mr. Coates to put in a green filter, so it just passes green light. Now, you see that green being reflected from this white surface. You'd say, of course, if you put a green filter in front of white light, you expect the light to go green, don't you? I mean, there's nothing very clever about that. There it is. But did we really need to put that filter there? You watch this green band here and just concentrate on it. Let's take the filter out. You see, it hasn't changed. That green band was there all the time. It wasn't the filter that made the thing green at all. What the filter did was to take away all the other colors. And I think that's a rather important thing for us to remember. I think it was Newton summed it up roughly in the words that the color belongs to the light, not the object, the light by which we see it. Well, now, just before we leave the spectrum, I will just have you, we've seen these photoelectric cells. I'm just going to use it quickly just to show you that we can measure the energy of the spectrum. And if we could just dim the lights once more, I'll just run it across quickly, and you should be able to see the meter on the screen. There it is. And as I run this across, you will see that very approximately it's what we would call an equal energy spectrum. There's a bit more up here in the yellow, but very roughly it's equal energy. If we could just put the red filter in once more, Mr. Coates. Thank you. Now we get nothing, 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 as you would expect, until we come to the red. And so we could go on putting different colored filters in, thank you. And each time, each filter we put in that removed various colors of the spectrum, we'd find there was a different distribution of energy. And each time we put different colors in, we'd see a different colored light. So we might think that in order to know what color it is that we wish to transmit, what we need to know is exactly what wavelengths we have removed from the spectrum and what wavelengths we have left there. There's almost an infinite variety, isn't there? We can add and subtract. And indeed, if we really had to describe accurately the way in which we had added or subtracted energy in different parts of the spectrum, I don't think we'd have ever had color television or photography. It would have been far too complicated. But fortunately, for us, because of the way in which the human eye sees color, it's possible to match virtually all the colors around us using only 3 sources of light, 3 primary colors, red, green, and blue. Now, I'm going to demonstrate this. We've got 3 little projectors here. I'll just squeeze through and get on this side. But before I actually demonstrate it, let me just clear up one little possible misunderstanding. I've said 3 primary colours, red, green and blue. In the art classes, you've probably heard of 3 different primary colours. Yes? What do you call the primaries in the art classes?
Red, yellow, blue.
Red, yellow and blue. Fine. And what happens when you mix yellow and blue?
You get green.
Green. Well, now I'm going to show you in a minute that when we mix yellow and blue, my primaries, you're going to get white, which sounds all wrong, doesn't it? Well, now what you've got to remember, and I want you to remember this, that we're dealing with a different thing here. We're dealing with adding coloured lights. We're starting off, if we put all the lights out, with a dark screen. We won't put them out for a moment. And then we put on the projectors and we're adding light. And gradually we're building it up. And when all 3 are there together, we'll find we get white. In fact, if yellow and blue are together, we'll get white. We'll show you why. But when you're painting, you're starting off with a white background and you're subtracting. Every time you put down a layer of paint, you're subtracting something. So if you put down all your 3 primaries, the art primaries, you finish up with black. If you put down the ones I'm going to talk about, you finish up with white. Mine are called positives. The ones you were talking about were called negatives. And now on with the demonstration. Down with the lights and let's put on the patches and see if it works. Here's a red patch. And now I'm going to put a green patch on top of it. And just as I said, red and green together make yellow. Now a blue patch. And now you see, in the middle here, where they all overlap, it's tending to be white. I will say right away, here and now, under these conditions, it's quite difficult to get everybody to agree what we call white exactly. That looks to me to be a little, perhaps too red. Is that a better white here? Well, anyway, we won't all agree. You know, the people that make the detergents, they all have totally different ideas, haven't they, about what's white? This is whiter than white, and, well, this is white. Okay, that's adding them. Now, I'm going to take this card away, and behind it, you'll see what happens if we have an illuminated source behind, which is shining light through these filters I was talking about, just cellophane filters, as if they were layers of paint. And I'll take it away, and you see exactly the opposite happens now. Now we have black in the middle. We have these negative primaries, the one you spoke about, calling that red, blue, yellow, and we have our positive primaries where these overlaps occurred. So they're the negative primaries. I'm going to talk about these, the positive ones. So we'll have the light down again, and I'll just twiddle these things about and show you that if we superimpose them, fine. Fine. Well, now, I can alter the intensity, and as I'm doing it, well, we can sort of make these very dim and start off with blue. I can reduce the blue, and I can bring up some of the green, I can bring up some of the red, and we can, in fact, play around. I'm not doing anything special. I'm just producing a lot of various colors. But I can assure you that if I mix them properly, and we'll do it more professionally in a minute, we'll be able to get nearly all the colors we see around us. But I think you're going to say that I could play around with those until I was blue in the face. It's an unfortunate expression when we're talking about color, isn't it? And I'd never get brown. Well, in fact, brown isn't really a color at all. Now, that may surprise you, because we all regard it as a color, and I can see people who would say, well, look, I've even got a brown pullover on. There's one over there. But brown isn't a color in its own right, and I think we can demonstrate this. I'd like some help here. A young lady's going to come and help me, yes? Right, now a little switch here, and at the moment we're going to switch everything off, and we'll lower the lights, and I am going to switch on a nice bright orange patch. Now, as soon as the lights are lowered, in fact, there it is, lower the lights. There we go. Now, I think you'd all agree that this sort of colour is by no means brown, is it? It's a reasonable sort of orange, yellowy orange patch. It's quite a nice bright patch, and I'm going to reduce its brightness only, not change its colour, just by dropping this filter in here. And that hasn't changed its colour, it's just made it a bit darker. And I think you'll agree it still is an orange patch. Now, when I say 1, 2, 3, go, I'm going to switch mine off and you switch yours on. 1, 2, 3, go. Now you see, this is the reverse thing. This has got a white thing all the way around and a black patch where my orange one is. And now I'm going to switch my orange one on, and I think you'll agree that that is brown. I'm going to ask you to switch yours off, and let's see if it goes orange. It does, doesn't it? On again. Brown. I think that deserves a clap, don't you? Thank you very much. So you see, we can produce these muddy colours, and brown's one of them. Why it looks brown is not because it is one of the colours we see in the rainbow, but because it is an orange or a yellow colour that is seen in contrast with brighter things around it. And it would not look brown if it were not seen in contrast with brighter things. Well, now I told you I was going to come to a more professional colorimeter. Well, actually, this is a very ingenious one. It's built for demonstration, but I think it will show us some rather interesting things, and I'll just explain it first while the lights are up. We'll get it into the right position. If I said to you now that we can use 3 coloured lights in different proportions to make up any of the colours we see around us, and if I said over the telephone to you, look, I've got a marvellous colour here, it's an absolute beauty. It's 20% red and 30% blue. Would I have to say anything else to you for you to know how much green? How much green would there be? 50%. So I only have to say 2 things, haven't I? Well, in actual fact, the 2 things that we choose to say are how much red and how much green. And we don't bother to say anything about blue in this diagram here. If you think of that as being how much red, and that as being how much green, and that is 100% red, and that's 100% green, we can start mixing reds and greens, and provided they all add up to 100%, they're going to lie on this line, but if we bring in some blue, it's going to pull the colour over towards this corner, so you can regard that as the blue corner. But it isn't plotted as such because, for the reason I said, if I tell you how much red, how much green, you know how much blue. And this is how this works. We're going to see the amounts of red, green and blue on this triangle. They're mixed together to form the colour on this patch. And here I'd like some help, because what we're actually going to do, where's Edward? He's going to help me. That's right, Edward, you come round. You're going to help me, aren't you, with plotting these colours. So we'll switch this on, put the lights out, and we'll plot some colours. Let's start off with it. Well, now I'm going to start off with it right down in that bottom right-hand corner. Now the whole thing is red, so it's right along here. Where are you going to put the red one, Edward? Can you reach? Absolutely, right. Now we'll follow up this line. We'll take away some red and add some green, and I'll stop about there at that orange colour. Where you put that one? Just about there. Lovely, right. Move it on. That's the halfway mark, half red and half green. That makes yellow, doesn't it? We saw that. Fine. And we'll now go right up to green. Where does that go? At the top, yes. And now if I can turn the 2 knobs at once, I can come halfway down here, half blue, half green. That was the bluey green, wasn't it, the man was trying to describe? Put that one on. Lovely. And down to the bottom. And now it's all blue. And if I were able to go on, I'd be running into that ultraviolet we talked about, according to the spectrum. Well, Edward has, for us, plotted some colours on what we call a colour triangle. Thank you very much indeed, Edward. Thank you. Supposing I hold up this white one, where do you think that ought to go? Any idea?
In the middle.
In the middle. Why do you think it ought to go in the middle?
It's 33.3% of each.
33.3% of each. Absolutely right. A third, a third, and a third. So we don't have to say anything about the blue one again, but it's a third of that and a third of that, and automatically it lands up right in the center of gravity in the middle of the triangle. So there's white. And there's one more color that isn't in the spectrum, but we see around us, whenever you get red and blue mixed together, you get a purple, and it lies along that line. Now there is the color triangle, and that's how we plot them. So now we're in business because we're beginning to measure color. In actual fact, the way in which it has been internationally agreed to measure color is to use a color triangle like this, but with a few modifications. Before I show you this, I'll pull it over. I'll just make one point to you. Do you see that as we move towards the center, the colors are going to get whiter and whiter? Because white's in the middle, and the more of that I have, the paler the color is going to become. These around here are the colors of the spectrum, the rainbow as we started off with, red, orange, yellow, green, indigo, blue, etc. White in the middle. Now you could go on drawing triangles, but all the ones inside would be paler and paler. And this you will see on this box. If we now lower the lights and put up the, there we are. It isn't accurate, but it gives you an idea. There are the bright colors around the outside, white in the middle, and they get pale as they go towards white. Thank you very much. Well, now we know that we can make up colors using red, green, and blue. You might have said, well, now, why didn't you just start off with this? Why all that nonsense about the spectrum? You could have said that at the beginning. But you see, we have to remember, and I think it is important to remember, that we are only reproducing the sensation of the color. We're not really producing the true physical color in the sense of repeating its spectral energy, as we call it. It doesn't matter. It produces the right sensation, and that's why we get away with it. But it's only fair to remember that the spectrum is the correct view. Now, I've got a box here that takes advantage of the fact that we can use photoelectric cells, and one of them can be designed especially to be sensitive to red, another one to green, and another one to blue. And you know what photoelectric cells do? They produce electric currents according to the brightness. So each one can send a signal down one of three wires and say how much red, how much green, how much blue is there, if I use all three of them. And at the other end, I'll just move this over. At the other end, we can use these currents to light three electric lamps. One red, one blue. I'll switch this on. And first of all, let our three cells have a look at a white patch here. There's the white patch. And there we are. They all light up as we would expect. Now let's go on to the blue patch. Fair enough, just the blue ones are light. There it is, blue. Onto the green. There's the green one. And one stage further onto the red. And there's the red one. So if we are getting the others lighting, it's because of the very bright light is leaking in under here, but there it is, there's the red one. So this is actually now able to measure the color, as it were, and send it down and reproduce the appropriate proportions as it lights the other end. Well, we're practically there, aren't we? We're nearly now able to think in terms of colored pictures, excepting, of course, we've got to do it all very quickly. You see, if you think of these little picture elements I talked about, the 500,000 or so that are transmitted on the face of the tube, or the 11 million that go out in every second or so, each one of them we have to say how much red, how much green, how much blue. And at first sight, it may seem that we're going to have to send out a lot more information and use up a lot more spectrum. Well, let's first of all borrow from what we already knew from photography, that in order to do this, the simplest thing to do is to just use, as it were, in three cameras at the sending end and three receiving tubes at the receiving end. You see, a simple way of achieving color photography is to take a black and white camera, or three cameras if you like, and take one picture with a red filter in front, one with a green filter in front, and one with a blue. needless to say, these filters have to be designed exactly to match this sort of response of the human eye. They've got to be very carefully designed, but if we do that, then we will have three images we call the red, green, and blue separation images. And the other end, if we project these three images, making sure we use three projectors that superimpose the images and see that one of them is red, one of them green, one of them blue, we ought to get a color picture. Now I'll go around the front here and we'll see if this really happens. If we can have the lights down, I'll start off by switching on the red one. Now it doesn't look red because it was a black and white camera, you see, that took it. But you do notice that it was taken through a red filter, and the girl's lips, which are red, are probably as bright as any part of the picture because red was the color that was going through the filter, so her lips are now quite bright. Let's switch that one off and have a look at the green result. Well, now you see the reverse has happened. Her lips are looking very dark, her skin tone is wrong. That's how she would look. They're the brightness values of the green signal, not true to life. And worse still, if I put on the blue one, it's going very wrong, isn't it? It looks as if she's been out in the sun for too long. Right, well now, this time I'm going to put in the red filter in front of the red projector, switch that one on, and there's a red image. Now you can see that in the monitor. It's not a very strong image, but it's strong enough. There it is, quite clearly a red image. And now we'll switch that one off, the green one on, and I'll put the green filter in, and we'll now see a green image. Well, that, I think you'll agree, is a brighter image. Green is a brighter color than red. Switch that one on, off rather, and have a look at the blue one. This will be very dim indeed because the eye isn't sensitive to blue, and it'll indeed be quite difficult to see that. There's plenty of energy there, but the eye is very insensitive to blue, but there is a blue image there, and it's very important to have it there. I'm now going to switch them all on together. Now, as I do so, let's have the lights down, on, and we have a normal color picture built up of those three separation images. Fine. Well, this is then, I'll switch them off. This is then what we have to do. We have to, in effect, use three cameras and not one. That wouldn't be very convenient, would it, to actually have three cameras in the studio? Fancy trying to make them all simultaneously look at the same scene. No, we must have a single lens and somehow arrange that the image that we want to transmit goes through the one lens and is split up into three separate images. We could use these filters, but we'd be throwing away an awful lot of light, wouldn't we? Because if red, green, and blue added together make white, and now we want one of the cameras only to see red, we'd be throwing away 2/3 of the light if we threw away the green and the blue. So a very inefficient way to do it would be to throw away the light using those colored filters. But fortunately, as so often happens in this marvelous world, physics provides us with a better way of doing it. Now, have you, yes, thank you, I'll take it. Have you ever noticed that you get a puddle in the road and some oil has run down from a motor car with a leaking sump or something, and you've got this thin film of oil, and you get these marvelous colors on the surface? Have you ever known how those colors come about? They're because the wavelength of light, you see, which I've already talked about, we're talking about something less than 1/1,000,000th of a meter, but it's comparable with the thickness of the oil layer. In fact, the oil layer is thinner than that. Suppose, for example, to something in the middle of the spectrum, say yellow light is a typical example, something fairly well in the middle of the spectrum. Suppose to yellow light, the thickness of the oil layer is just 1/4 of the wavelength of the yellow light. Now, the oil is a different medium to the water, and so when the light goes through, it'll be reflected from the surface because there's a sort of a discontinuity, there's a junction there, so some will get reflected. And since it's 1/4 of a wavelength long, by the time it's traveled there and back, it's a 1/2 a wavelength, and that means that the light arriving is going up and down, and the light coming back is going down and up, and the two things are cancelling. And so we've lost the yellow, and that's left us with blue, yellow being red plus green. Now if you think of different thicknesses, you can work it out and you can see that you can get all sorts of wonderful colours depending on the exact thickness of the oil layer. If we do this in a very controlled way by making very even, thin metallic layers on the surface of perfect flat pieces of glass, we can actually make what we call dichroic mirrors. And these are mirrors that, with this interference property, not now by using pigments and colouring the mirror, but by interference, they are producing various colours. And they have this very interesting property that they reflect one part of the spectrum and transmit the rest. And if you add the two lots together, you haven't lost anything at all, or virtually nothing, 99.9% of it, if you add what is reflected to what is transmitted. And here is one of them, which is transmitting green. I'll put it in front of my face. Do I look suitably green, horrific? That's transmitting green. Now I'm going to see if I can reflect into this camera here without doing it too much. I'll just come gently down. Now can you see it's reflecting purple minus green. So green is being transmitted and purple is being reflected. I'll just do that once more. That part of it, you do see that is green when I look through it. Well, by using this property of dichroic mirrors, we can arrange to split the image into its red, green and blue components and not lose any light. And I'll just help Mr. Coates out with this machine. And while he's fixing up the screen, let me explain what it is. This is just a projector that's going to shine some white light through the hole, which will go straight through onto the screen. It's ordinary white light. But these things that I'm going to let in the way in a moment, you'll see them drop now, are the dichroic filters. Well, I'm letting down the middle one. That's all I need do. Just the middle one is enough to expose the hole. Now, before I switch it on, I'll follow through the argument with you so that we can see what's going to happen before it happens. I'll leave it down just to illustrate the point. There it is down. Now, the light will come through here. It's white. And this mirror has the property of reflecting red, and it's at 45 degrees, and so the red goes down here, and it goes onto this mirror, and it goes shooting off onto the screen, so that's red. Now, since it's reflecting red, and nothing's being lost, it must be passing green and blue. So it goes on in this direction, and this mirror, this one, has the property of transmitting green, but reflecting blue and red. But there isn't any red, is there? That got shot off down in this direction. So the only thing that goes up here is the blue, and that hits this ordinary mirror, and it goes shooting off onto the screen in that direction. If everything's working properly, that's what we ought to see. So I'll switch it on and down with the lights. I'll pull up the screen first, pull up the filter first. There's our white light, and there it is, split into its red, green, and blue by these mirrors. Just do it once more, take it away, prove it's white light, red, green, and blue. Fine, thank you very much. Well, you see these cameras around us, you couldn't really miss them, could you? There they are. That's what's happening inside, and of course it's happening on a smaller scale. It all has to fit inside that box, and this great dichroic display I've got here is all condensed down to a very, very neat optical block. So I'm going across to the camera, and perhaps if I speak very nicely to Roger here, he's going to let me have a look inside, or let us all have a look inside. This is a great privilege. This is the lens here, and it's a great lens which goes through the middle of the camera, a great zoom lens. And now if we undo the side, we're being very privileged having a look right inside. These are the camera tubes, these things, and I can't really get to it, but right in the middle there is that optical assembly of dichroic filters that splits the light up into its red, green, and blue components. There's the camera, and there's all the electronics, and it all fits inside the box. Thank you, Roger, for letting us have a look inside. That's very good. So, now, so much then for the color camera. The color camera can provide us with 3 signals, and they could be sent along 3 wires, sent to the receiving end, but then we'd need 3 television receivers if we were going to do it in the way that we'd just seen it done with those projectors. That we don't do, you know. We look at a single cathode ray tube, and it looks like an ordinary cathode ray tube, but of course it isn't. It's a clever one, and it's a very clever one indeed, and I'm now going to show you how it works. It's called a shadow mask tube, and thank you, Bill. And this is the shadow mask. This is the magic piece, and I'm just going to ask you, you hold that for me, Mary, and I'll swing it round first of all. Probably that way is the best. And I think you'll probably be able to see on the monitors the light shining from up there is illuminating little dots, red, blue, and green. There they are, all arranged in triangles. Well, at the moment, we've got light shining from this side, but the way I'm going to demonstrate it is light shining from this side, and if I switch on the switches 1, that's lit this light. Can you see that? That's shining onto my hand there. Switch on this one, and it's this light, and this one is this light. But all those 3 lights are simply going to shine on the back of the screen, and it's not going to make very much difference, is it, whether I have 1 of them on or 3 of them on. Now, before I turn it round, let me explain something that I'm sure you can already guess. In practice, what our light beams are going to be electron beams inside the tube, and these little transparent red, green, and blue dots are going to be the phosphors on the end of the tube, specially arranged that 1 phosphor glows red when it's bombarded, 1 green, and 1 blue. So imagining that these are electron beams, we'll now turn it back again, and we'll try and get a good shot of the front of it. I'll switch on the 3 switches, and we'll have a look at the front. We'll need the lights down. Can you see red, green, and blue dots? Yes, you can. And if I can find the switches, I can switch 1 off, or another one off, another one off. Nothing happens. It may go a bit dim, but because we're not putting so much light on it, but nothing happens. Now let me have the shadow mask back, Mary. This was the magic. And I'm going to slide this in, and I want you to see what happens. There it is. Now, it's gone a little dimmer, but now, when I operate the switches, that one switches off red, that one switches off green, and that one switches off blue. We have separate control over those 3 sets of dots, red, green, and blue. So by aiming the electron beams through that shadow mask, thank you, we'll have the lights up, this color separation is achieved. You can just imagine it focusing the 3 beams through these holes and them landing up just in the right place when the total number of dots on the tube is around about 1 million. It's pretty marvelous, isn't it? It's a wonderful piece of engineering. Now I'm going to show you, you've seen the model of the shadow mask tube, and now I'm going to show you the real shadow mask tube, the sort of thing that we've been looking at these pictures on, and we have one here. And if I use a magnifying glass, you may be able to see the little colored dots I've been talking about. So I'll use a magnifying glass, and I'll set it in here, and if we hold it at the right distance, I'll start off with the red by itself. Now, can the camera pick up those red dots? Okay, you can see those, that's good. You may see the green ones even better because, as I said, green is a brighter color than red, and they're very clear, aren't they? They're just the green dots being illuminated. Now I'll switch on the green. Now remember, blue is a very dim color to the human eye, and also the ability of the eye to see fine detail in blue is very poor, so you'll have difficulty in seeing those, but they're there, red, green, and blue. And I can switch them on and do the color mixing just as we did before until we come up to white when they're all on. See the monitor again. So there's our cathode ray tube. Now, in actual fact, I said we could send 3 signals, red, green, and blue, to the receivers. But there is just one snag. If we were to do that, we'd need to use 3 times much of this terribly valuable ether space that we talked about. And also, we'd need to have, in effect, 3 transmitters. And worse still, all the people who had black and white receivers wouldn't be able to receive the pictures because we'd be sending out 3 images which were, no one of them was a correct representation of the black and white picture. Now, do you remember when we were looking at that color diagram, I said that the bright colors were on the outside, and as we moved toward the center, they got paler and paler. Well, there are 3 different ways in which you can describe color. You see, if you have to say 3 things about something, you very often find that you can transform them into another 3 things which gives you the same information. And the 3 other things that we can use are terms which are very familiar to us, and we use them in daily life. We talk about the brightness of an image, how much light there is falling on it. And then we talk about its color, that is the hue, the color, where it is in the spectrum in physical terms, and its saturation, and that is how much it's diluted by white. And if it's very diluted by white, it's a very pale shade. If it's not diluted by white at all, it's fully saturated. Now, if we choose to send one of those things, brightness, and the other 2, just describing color, we find that the amount of information we have to send is very much less than it would have been the other way around. The additional information, color, doesn't have to go at nearly the same, use up nearly as much bandwidth because the eye isn't very good at seeing color on its own. It relies on brightness. You can afford, when you're painting color in, to be careless with your color. Color printing very often relies on the black and white outline and puts the color on quite carelessly. So I'm going around the front just to demonstrate this, and I'm going to show you 3 slides, and you'll be able to see them on the monitor. The first one is a black and white image, and that's the black and white image that's being received. You can see them on these monitors by itself. Now, the next thing I'm going to show you is color only, not brightness, just color. And it's a very strange thing. You may have never seen this before. All those colors have roughly the same brightness. And it's just color, and you see how blurred it is. It isn't a sharp, clear image like the other one. But if we add the 2 together, that's the result, and you get a fully colored picture. So that's the way we have to do it. We send out brightness and 2 other pieces of information which fit in very nicely, very cleverly, in the same bandwidth at the top of the band where it doesn't matter very much, and the color receiver can receive those and get color. Well, now I'm going to just do a little bit of a trick, and in fact, I come around the front again for this. Who hasn't been abroad? Who would like to go abroad? You'd like to go abroad. Well, do you just stand over here, and that's right, just stand there. I'm going to sit down here, and look, there's a choice. You tell me. Where would you like to go?
I'd like to go to Moscow, please.
What number's that?
Number 6.
Number 6. Moscow, he's there. Excellent. Very good. Like to go anywhere else?
Yeah. Can I go to Mount Everest?
Where's that?
Number 11.
Number 11. Fine. Who hasn't been abroad? You haven't. You haven't. You come down. There's a good reason for being careful about it. I'll tell you about this later. You may be able to work it out, but you come down. You stare him down, Richard, and show him the sheet. You're the travel agent. You ask him.
Where would you like to go?
He's not sure.
Choice. Italy. Nice Italy.
Egypt.
Egypt.
Please.
Number 5, please.
Number 5. There we go. You're in Egypt. How's that? Well, that is one of the tricks we can do with colour. Thank you very much, Richard, and thank you. And your name is?
Ian.
Ian. Thank you, Ian. Now, who likes to do painting? We've got an artist here. Who's the artist? You're the artist, are you? You look as if you are. If you're going to do some painting, you'll need a smock. So I'm going to put this smock on you. You're going to get yourself in a mess if I don't. Which way around? Ah, yes, you're probably doing better at doing this than I am. Fine. I think you ought to have an artist's hat, don't you? There we go. Worn like that. Very splendid. You can see yourself on the monitor. Good. Right now, you stand just there, and there's your pot of paint, and I want you to paint us a really beautiful picture. And occasionally, you can take a look up and see how you're doing. All the best artists do. He's coming, yes. Did you expect to paint that?
No.
What are you painting? It looks to me as if you're painting, is that Egypt? Venice. Oh, that's a surprise. She's painted Venice for us. That's absolutely splendid, yes. Paint all around the edges. I've got another white card, have we? Would it reverse? Would it turn over?
I think we've got no problem.
You know, I think you ought to paint a masterpiece. That was very good. I'm not complaining. But if we can turn this over, I'm going to get you to paint another one. We've just about got time. I think you'd get a good price for Venice, but, you know, they're very common, these, you know, these sort of things. But let's see what you get if you try and paint this one. See if we can get a masterpiece this time. Have another go. Now, this is beginning to look more like a masterpiece, isn't it? I say. I think you could really sell this one for some money. How's it going? You can see it. Oh, can you recognize it? Do you know what that painting is? It's a very appropriate painting. Do you remember we started off with Christopher Columbus? Well, that's a very famous painting indeed that Kay has painted. It's The Boyhood of Raleigh. And there he is pointing out across the Atlantic. What a splendid... Can you paint pictures as fast as this always, Kay? Well, I think that would be worth a fortune. Let's have another look at it. Isn't that absolutely splendid? Well, thank you very much, Kay. Well, now, you see, in this lecture, what we have done is we've really brought things, or I've tried to, from the beginning when we just were able to deflect a compass needle with an electric current, when this first discovery was made, and we've gone through to see how messages could be sent, how we could not only send messages along wires, but through empty space. And we've gone on to see how the messages could be sound, or they could be music, how indeed they could even be pictures, and how we have finished up by sending color. I'm not going to explain that last trick to you, but you might be able to guess how it was done, especially as you saw our Richard and his friend both go abroad. But that is the sort of thing we can do, and I think that sort of brings us more or less up to the present stage, the present day, where we came in, if you remember, and we saw those fantastic pictures of Neil Armstrong landing on the moon. I say. Now, they didn't tell me they were going to do that. That's not Neil Armstrong. And there was Neil Armstrong landing on the moon. There's the moon. And we had those fantastic pictures back. Well, we really sort of... I don't know what they're doing, but I'm going on talking in spite of it. What we've done is we've pieced together this jigsaw puzzle we talked about. And I think we could fairly say that we've brought it up to the present stage, the present state of communications, certainly as far as sound and vision have gone. Now, in the next lecture, I want to talk about some of the new pieces of the jigsaw puzzle that are coming along, show you some of these, and we're going to try to see how they're going to fit together. You're the ones that are going to have to fit them together, but the idea next time is to have a look at them and see what scope there is to do further things in communications. Thank you very much.